I'd like to give a quick review of conductors and their interaction with E fields, and then go on and talk about capacitance. So if you remember from beginning physics, the E field inside a perfect conductor is equal to 0. And so if you place a conductor into a region where you have an E field, the free charges in the conductor will move under the force that's produced by the E field on any free charge. We're stating that the E field that results inside will be 0 because it cancels the external field. The separated charge produces a field to cancel the external field. So one way to look at it is we're dealing with electrostatics. So if you had a field inside, the free charges would move in response to the force that I just mentioned. If you establish steady state, the field inside will be precisely 0. There's another property that you might think of, and that is polarization, because that's really what this charge separation involves, and that leads to the concept that a perfect conductor is a perfect dielectric, and we'll discuss that later. So let's look at part B here. Suppose we have a charge density ρ that is inside. It will be equal to 0. So ρ is equal to 0 in the interior of a conductor. If we look at the differential form of Gauss's law, which you're familiar with, this is from Maxwell's equation 1, then the charge density is related to the divergence of the E field. So if you have a charge density, you will have a divergence that's non-zero. So if you look at the case where we're inside, we have E equals 0, so therefore it has no divergence. You end up with a 0 charge density. So as a consequence, no excess free charge exists within the conductor. So as a result of this last conclusion, that there's no charge inside, we can say that any net charge or any unbalanced charge will be on the surface. So let me just make sure we understand that when we have a conductor that's neutral and there's no E field, there are charges, of course, but they're all balanced. We don't have any net charge in an uncharged conductor. If you apply an external field, you can't change the total charge of the conductor, but you can displace, well, in the case of metals, electrons in the material. So if the E field is such that it wants to move negative charge in this direction and positive charge in this direction, so in other words, the E field is in this direction here, so it's pushing on positive charge, then what happens is that you will get negative charge here, positive charge here, and that'll create an extra E field that's in this direction. And so if there's an E field here, initially charge will flow, but it will stop flowing when these two fields balance, and then you have 0 charge here. So where is the charge? Well, it's on the surface. Okay, another item is that the potential V is constant everywhere on and inside a conductor. Well, this goes back to the case where if you didn't have this condition, a current would flow, distributing charge from one part of the conductor, and so that you'd end up again with not electrostatics. So in the steady state where you have no current, the charge distribution on the surface must be such that there is no potential differences anywhere in the conductor, including 2 points on the surface. So in other words, if you have this condition here, where this quantity here, which of course is defined in terms of the E field between 2 points A and B as this integral, because E has to be 0, then you'll have this potential difference equaling 0. So that means then, for example, if you have this conductor here, we know that E is equal to 0, and we're concluding that delta V equals 0. Then if you have static charge out here put onto the surface, then if you take 2 points on the surface, there will be no potential difference between them, because otherwise charge would flow on the surface. You consider then that the conductor surface is part of the bulk conductor. If you put charge on the conductor, you can think of it as being external to the conductor. Only the surface and the bulk are tied together and have the same potentials. The charge resides, well, let's say just a hair outside of the surface. So all fields that are coming in, say, from external charges are terminated by these charges here. So let me repeat, this is just a simple way of thinking about how you could have zero field and zero potential difference along the surface relative to the bulk material. So it's just a convenient way to think about where is the charge and where is the conductor so that it behaves the way we're saying. Okay, so the E field that we get has a certain orientation to the surface, namely it's perpendicular to the surface. And so just to remind you, the line integral of E for a closed loop is equal to 0. Remember, this is in agreement with the conservation of energy. In our case, we're going to have a surface charge which is non-zero to make it interesting. So that means that if you have a surface, suppose this surface here has a charge density sigma, we're going to draw a loop along the surface where the height of the loop is very small. This epsilon is the distance here. L is the length of the loop, and we'll make it small enough so that the sigma doesn't change significantly over the length of that loop. And remember, here this is above. We'll say that it's in air or vacuum, and below is in the conductor. Well, we know that if we look at below, E below is in the conductor, then we would have the case where if we took an integral of this around this loop here, that we're going to end up with 0 because we make the entire loop. So if we make a closed loop, then we'll get 0. And that comes up here. In agreement with conservation of energy, the line integral of E for a closed loop equals 0. We make epsilon small so we can ignore any contributions to this integral on those ends. What's left is that we have all our E dot dLs along the parallel portions, and so we'll just write that as E parallel dl. So we've got one of these above and we got one below. However, remember that below we have E below being inside the conductor, so therefore that contribution will be 0. So we made this L small enough so that sigma is constant over the region near the curve C. So E above is constant given by this expression here, which we've derived. The E above magnitude is sigma over epsilon naught, and this is the uniform sigma. So we can then go back to our line integral, which we've said is equal to this. The only component that's left is this constant E above times the length L. That's the integral. And then everything is 0, which comes from the fact that we have this conservation law here. What we end up with then is that the parallel component of the E field is equal to 0. So what that means is that the field above only has the perpendicular component. I'm ruling out the case of E equals 0 because it's just uninteresting. We conclude then that the E field is always normal to the surface of a conductor. We're ready to attack capacitance, and let's consider two conductors that have two charges, plus Q and minus Q. We know that there will be an E field between them from the plus to minus charged conductors, and the charge will distribute itself along the outside surfaces of these two objects. Thus an E field exists between the two conductors. That means there's a difference of potential between them, because if we integrate from one conductor to the other, the E field dot dl will get a potential difference. We've already said that V is constant over the surfaces of each of these conductors, so we can just give those a value, and we'll call these V plus and V minus corresponding to the plus and minus charges. We know that we can write that difference in terms of the E field. If we have the E field between those two conductors, if we integrate from minus to plus, we'll get the V plus minus V minus of E dot dl, and that'll give us the difference of potential between these two conductors. The way I've drawn this, these are pretty messy surfaces, and so in general this E is a mess. Because of the lack of symmetry, you're not going to be able to calculate that E easily. In some cases, of course, we can. Let's take a look at the difference of potential here. Remember what the E field is in terms of charge density. It's equal to K rho, and then it's the funny R squared, funny R hat integrated over d tau. So let's set that up in terms of a picture. We have a region of space that has non-zero rho. outside, let's say it's 0. These vectors relate to some point, let's say outside, and a point inside. And remember, this is R prime, and this is R. So I'm putting my origin down here. So here's the origin. That's where these vectors come from, and funny R is the vector that goes from the source point to the field point. So this is what we called R prime, this is what we called R. But the important thing is if we're out here and we take this charge and double, say, the charge density everywhere, then what we've done is we've doubled the total Q. From this arrangement here is that if we double rho, then we double E. If we double Q, double rho, we double the E field. So our conclusion is that the E field is proportional to the Q that's contained in this volume here. Let's go back to the definition of the potential, and we'll just call that delta V, so it's equal to this quantity here. We've already said that E doubles with charge density, so if we double E because we doubled the charge, then we end up with delta V is doubling with the charge Q. We turn that into a proportion. Delta V is proportional to Q, or turning it around, the Q is proportional to delta V. So this brings us to a constant that will relate delta V to Q, and that constant C is the capacitance. So in other words, if you have a situation where you put charge on an object and relate that charge to the potential difference that created it, this would be the relationship, and C would be the capacitance. So we can rewrite that. C is equal to Q over delta V. Coming back up here, if we look at these two conductors here, if we were to put plus Q here, minus Q here, so we separate the charge, then we take the Q on one of them, divide by the potential difference between these two conductors, and calculate Q over delta V, and that will be the capacitance of these two objects. Where did the delta V come from? Well, that's the source of the charge separation. So you take these objects, so I'll just redraw them here. These are the two metal conductors. You put a battery between these, and so if I'm going to get plus, I'll make this one bigger and this one little. So what happens is that these objects, these conductors, will charge until the potential difference between them is equal to the battery. At that point, you've put positive charge out here, you put negative charge here. Because of the conservation of charge, you haven't created any new charge. Those two will be equal in magnitude with different signs. So that's what we did here. This is delta V, and these are the Q's, or the Q on this one minus Q on this one. So that gives us the relationship then of the capacitance that is developed between these two conductors. The units of capacitance are the units of Q over delta V. The name for that unit is called a farad. So 1 farad is 1 coulomb or 1 volt, and this is a very, very large capacitance. Usually we deal with small values. This is a picofarad, here's a microfarad. Millifarads are still pretty big, so be careful with that size of capacitor. We say P is equal to pico, and that's 10 to the minus 12. So how do we derive the capacitance of, say, a two-conductor system? Well, I'll give you a recipe. Suppose we assume a potential difference and then determine the charge on each conductor. And actually we are only considering the Q, which is the magnitude of this. So if you have that arrangement where you start with this and calculate Q, then of course you can calculate the capacitance. The other way is to assume that you know Q and find the potential difference between the conductors. And there again, you just take the ratio to get the capacitance. So here's a picture here. So we have some conductors here. We're given, say, the potential difference. So we're given like a battery across these two plates. We determine Q, and then we can find C. Then the inverse is that we're given Q. We determine the potential difference, and again calculate C. Again, remember that C in vacuum or air will depend only on geometry, things like the spacing. So let's look at the capacitance of a parallel plate capacitor. I'm sure you've done this several times, but let's go over it carefully and try to get the full set of logic that we're going to use. The first thing is we've got to look at the assumptions. So here's our parallel plate capacitor, which you're familiar with. Area A. We'll take this as being square, so this length here is the square root of A. D is the spacing, and we put plus and minus charges on. And the reason we do that is because if you were to take a battery and put it between here, so let's just say this is plus and this is minus, we have this delta V here. Realize that charge can't be created or destroyed. So when you hook this up, whatever charge you pull off of this plate has to go onto the other plate. Well, if we believe in electrons being the conducting charge, then pulling electrons off of here will push electrons over to this plate. And that's the purpose of a battery, is to do this little dance. Well, if this leaves plus Q behind, it means that this surface here received minus Q. These are simple assumptions. D is a constant everywhere. The charge is uniformly distributed so that the charge density is a constant. And we neglect edge effects, which will be a suitable assumption if D is much, much smaller than the length of one side of the plate. We define the surface charge density in terms of Q divided by A. And for parallel plates, we've derived this equation here, where E is the charge density over epsilon naught. Putting in the charge density, we have Q over A epsilon naught. This was derived from Gauss's law. So the voltage difference between the two plates is the E field that's inside times D. And that expression comes from the fact that the voltage as a function of x, the potential as a function of x, is given by this integral here, don't forget the minus sign, from 0 to x. Because E and dx are parallel, then this is just the magnitude of E times x, basically. So E is a constant, so we can write that. So if we let x equal d, we get this equation here. So we put in E, and we get this term here. So now we're ready to take the ratio. We have a Q, we have a V. We can take Q over V. Q over V, which is right here. Rearrange this, cancel the Q's, and we end up with this expression here. Now realize that this worked fine. This is great because we have no Q in this equation. We have no V. So we've cleaned this up until it's just a function of these distance and area parameters, geometry, and of course multiplied by epsilon naught. The parallel plate capacitor has the property that if you have a smaller D or a larger A, you end up with a larger capacitance. These two behaviors where you, for example, if you're after a large capacitance, then you either make the spacing or the area change like I've shown here, or you do both. It's important to realize sometimes you want a larger capacitance, sometimes you don't. Sometimes you like this to be as close to 0 as possible. So coming over here, you can think about how you might do that, either widen that gap or go to smaller A. If you're making very, very tiny objects, this one's okay, but this one is a problem because you're trying to make it larger. And so you have to be very clever in terms of the geometry and so on to reduce that capacitance. Just an example, sometimes you have a wire carrying information and another wire carrying information, and you don't want those to talk to each other. If there's a very high capacitance between them, then it's likely you will couple the signals that go between them. So that's one example where you're really trying to reduce this capacitance.